this study unit, we will describe PDP-11 addressing and memory organization. Let's begin by reviewing a few basic concepts. PDP-11 memory is organized into a series of storage locations, each of which holds 8 bits or 1 byte of data. In order to store or retrieve these bytes of data, a unique octal address is assigned to each memory location. Thus, the addresses 0, 1, 2, and 3 designate the first 4 bytes of memory. Although PDP-11 memory is structured from 8-bit bytes, we often deal with 16-bit words. To obtain words, we combine pairs of odd and even-numbered bytes as shown here. Thus, bytes 0 and 1 form one word, bytes 2 and 3 comprise a second word, and so on. Note that we call the odd-numbered bytes high bytes and the even-numbered bytes low bytes. Thus, each word consists of a high byte and a low byte. Let's see how we address these words and bytes. When storing or retrieving 16-bit words, we use even addresses only. Thus, the first 3 word locations in memory are designated by addresses 0, 2, and 4. We can also select bytes within any word. Odd addresses always select high bytes. On the other hand, even addresses select either low bytes or full words, depending on whether we're dealing with word or byte-oriented instructions. Words or bytes stored in memory can be addressed either by the processor or by devices capable of performing direct memory access or DMA transfers. Typical DMA devices include disks and magnetic tape units. As we noted earlier, PDP-11 memory always functions as a slave device. In other words, memory is passive. It can never address another bus device, nor can it initiate transfers between itself and another device. In order to function, memory must be addressed by the CPU or by a DMA device. Once memory is addressed, the CPU or the DMA device controls the type of data transfer that is to be performed. Now that we have reviewed some basic concepts, let's look at the major topics to be covered in this study unit. First, we will describe the format of the 16-bit PDP-11 word. Next, we will look at address assignments and memory mapping. We will then examine the various memory operations that can be performed in order to store or retrieve data. Finally, we will wrap up this study unit by describing the types of PDP-11 memories that are available. Let's begin by describing the format of the 16-bit word used in all PDP-11 systems. The 16 bits that make up the PDP-11 word are numbered 0 through 15, reading from right to left. Bit 15 is the most significant bit, or MSB. Bit 0 is always the least significant bit, or LSB. To simplify notation, we use a 6-digit octal number to represent our 16-bit word. In the example shown here, the word is represented by octal digits 154323. Let's take a closer look at this form of octal representation. Bits 0, 1, and 2 are grouped to form the least significant octal digit. In this case, the digit is a 3. Bits 3 through 14 are grouped in a similar manner to form the second, third, fourth, and fifth octal digits. Reading from left to right in this example, the resulting octal digits are 5, 4, 3, and 2. The sixth and most significant octal digit is formed by a single bit, namely bit 15. Thus, our 16-bit PDP-11 word has been reduced to its octal equivalent of 154323. Here are some additional examples of octal representation. Remember that bit 15 corresponds to the most significant octal digit, and bits 0, 1, and 2 correspond to the least significant octal digit. By the way, when we're working with signed numbers, the most significant bit indicates either a positive or a negative value. In our example at the top, bit 15 is a 0, signifying a positive number. In the second example, bit 15 is a 1, thus indicating that we have a negative number. We'll have more to say about signed numbers in the study unit covering the instruction set. As we noted earlier, each 16-bit word actually consists of two 8-bit bytes. Bits 8 through 15 are designated as the high byte, and bits 0 through 7 are designated as the low byte. We've just seen how octal notation can be used to represent our 16-bit word. In addition, we can use octal notation to represent a high byte or a low byte. Here, we see a typical 16-bit word represented by its octal value 125752. Note that the boundary between the two halves of the word falls between bits 7 and 8. This boundary must be taken into account when we assign octal values to high bytes and low bytes. For example, if we choose just the low byte within this word, the resulting octal value is 352. Note the difference between the octal value for the word and the equivalent octal value for just its low byte. The third octal digit is different because the low byte only uses bits 6 and 7. It does not use bit 8. Now, let's compare this word and its high byte. Here again, the octal values for the word and its high byte are different. This results because the bits are grouped differently. Compare each octal boundary in the high byte with its corresponding boundary in the word. In effect, the boundaries for each octal digit have been shifted one bit position to the right. In summary, the octal values for high bytes and low bytes are different from the value that represents the full word. Additional examples illustrating the use of octal notation are included in your workbook. As we noted earlier, a unique address is assigned to each memory location. This address is specified by a 6-digit octal number. High bytes are always designated by addresses ending in an odd number such as 014773. On the other hand, low bytes are designated by addresses ending in an even number, such as 014772. Word locations are also designated by even-numbered addresses. Thus, consecutive word locations are always addressed in steps of 2. Note that the address used for this word is identical to the address that was used for just the low byte. How then does a master device specify whether it wishes to store the entire word or just its low byte? Well, this function is accomplished by our data O and data OB transfers. If a master device wishes to store a full word in memory, it issues an even-numbered address and specifies a data O transfer. On the other hand, if the master wishes to store just the low byte, it again supplies an even-numbered address, but this time it specifies a data OB transfer. One final point. If the master device wishes to store a high byte instead of a low byte, it issues an odd-numbered address and again specifies a data OB transfer. As we explained earlier, our standard PDP-11 address consists of 16 bits. This address is expanded to 18 bits when memory management hardware is installed in our PDP-11 system. With the expanded 18-bit address, the most significant address digit is formed by bits 15, 16, and 17. The PDP-11 has only one set of addresses. These addresses must be used for memory, for the I/O device registers, and for registers contained in the CPU. Let's see how these addresses are assigned. Our standard 16-bit address provides 64K of possible byte addresses, or 32K of possible word addresses. Up to 28K of these word addresses can be used for memory. The remaining 4K of addresses are reserved for I/O device registers and for internal registers contained in the processor. These internal registers include the processor status word, or PSW register, as well as the general purpose registers. As noted earlier, we also have an expanded 18-bit address. This expanded address provides 256K of possible byte addresses, or up to 128K of possible word addresses. We allocate these addresses as follows. The last 4K of word addresses are still reserved for I/O device registers and for the processor's internal registers. The remaining addresses are available for memory. Hence, with an expanded 18-bit address, our memory space is increased to a maximum of 124K words. Since 2 bytes make up each word, we can accommodate up to 248K bytes of memory when we use our expanded 18-bit address. Here, we see the address limits for memory. With a 16-bit address, our memory space begins at 0 and increases to a maximum memory address of 157,777. This memory space provides storage for up to 28K words or 56K bytes. Remember, words and low bytes use even-numbered addresses. High bytes always use odd-numbered addresses. Now, let's take a look at the memory space provided by the expanded 18-bit address. With an 18-bit address, our memory limits range from 0 to a maximum address of 757,777. This yields a maximum memory size of 124K words or 248K bytes. Now, let's examine the top 4K of addresses. 16-bit addresses that exceed 157,777 are not used for memory. Instead, these addresses are reserved for our I/O device registers as well as the CPU registers. When we address these registers, the most significant digit is automatically forced to a 7 by hardware located in the processor. The processor accomplishes this by monitoring address bits 13, 14, and 15. Whenever these 3 bits are 1s, it signifies a register address. The processor responds by placing 1s on bus address lines 16 and 17. As a result, the most significant address digit is converted from a 1 to a 7. This conversion places all register addresses in the last 4K of our total address space. Notice the gap that occurs between our highest 16-bit memory address and the register addresses. This gap allows for possible memory expansion. In other words, at a later time, we can use the expanded 18-bit address without having to modify our register addresses. Here's a typical 16-bit register address. Note that the original address is converted to 772520. The processor performs this conversion by taking the most significant digit, in this case a 1, and forces the digit to a 7. The remaining digits are not changed. The address resulting from this conversion falls within the last 4K of our total address space. In this example, the address designates the status register located in the TM11 magnetic tape interface. Similar conversions are performed for the other 16-bit register addresses. Before going on to our next topic, let's briefly compare 16-bit and 18-bit addresses. A 16-bit address can accommodate up to 28K words of memory. In addition, 4K of address space is reserved for our I/O and CPU registers. When we're addressing these registers, the most significant address digit is always forced to a 7. PDP-11 systems that are equipped with memory management use an expanded 18-bit address. With an 18-bit address, we can have up to 124K words of memory. One final point. Note that our register addresses are always located in the last 4K of the address space. Because of this arrangement, we can add memory management hardware to an existing PDP-11 system without having to modify our register addresses. A typical PDP-11 memory has specific areas set aside for certain kinds of information. Defining these areas is called memory mapping. Let's begin our discussion of memory mapping by looking at the basic structure of memory. A typical PDP-11 memory can be broken down into the major areas shown here. The top area is reserved for storing the trap and interrupt vectors that we described in the preceding study unit. Following this reserved area is a space that is set aside for the hardware stack. The remainder of memory provides storage for users' programs as well as system and utility programs. Now let's look at each of these areas in a little more detail. Our first series of memory locations, that is locations 0 through 037, are always reserved for trap vectors. Let's take a minute or so to review the function of a trap vector. When certain error conditions occur, such as power fail, the processor automatically goes to a predetermined memory location and retrieves a trap vector. This trap vector then directs the processor to a specific error handling routine, which is stored in another area of memory. The processor retrieves and executes this error handling routine in order to service the error condition. When the error condition has been serviced, the processor returns to its main program. Each trap vector actually occupies two word locations in memory. The first word location contains a starting address or program count, which is loaded into the processor's PC register. This starting address directs the processor to the first instruction in the error routine. The second word location associated with our trap vector contains a new processor status word, or PSW. The processor retrieves this status word from memory and loads it into its PSW register. Once the status word has been retrieved, it establishes initial conditions that apply while the processor is executing the error handling routine. Here we see the possible trap vectors and the memory locations that they occupy. Remember, each trap vector requires two word locations. One location contains the starting address of the error handling routine. The other contains the new PSW. For example, the trap vector for power fail resides in word locations 024 and 026. That concludes our discussion of trap vectors. Now let's move on to our next reserved area of memory. Memory locations 040 through 337 are reserved for interrupt vectors. These interrupt vectors are retrieved by the processor when an I/O device interrupts in order to obtain service. Two unique memory locations are reserved for each device's interrupt vector. The first word location in memory contains the starting address of the device's service routine. The second memory location contains a new status word which is to be used while the processor is executing the service routine. The CPU retrieves this status word from memory and loads it into its PSW register. The area reserved for interrupt vectors can be further broken down as shown here. Don't bother to memorize this chart. It's repeated in your workbook. Memory locations 040 through 057 contain system software vectors. Continuing on, interrupt vectors for basic input-output devices, such as teletype or paper tape equipment, are stored in memory locations 060 through 077. Additional interrupt vectors for disks, magnetic tape units, and other I/O devices are located within memory locations 100 through 266. The remaining memory space is set aside for interrupt vectors associated with communications equipment. One final point. Note that certain locations are reserved for vectors assigned by the customer. In our chart, these customer reserved locations are shown in green. This concludes our discussion of interrupt vectors. A more complete listing of device interrupt vectors and their reserved memory locations is provided in the appendix to the PDP-11 processor handbook. The next area of memory is occupied by the hardware stack. As we noted earlier, this stack is used while the processor is servicing interrupts or traps. Let's quickly review the function of the hardware stack. The hardware stack allows the processor to temporarily store essential breakpoint data before going off to service an interrupt or trap. This breakpoint data consists of the current values in the PC and PSW registers. After the interrupt or trap has been serviced, the old PC and status word are retrieved from the hardware stack. The main program then resumes at the point where it was interrupted. As shown here, the hardware stack is located between the area reserved for vectors and the beginning of our user programs. The initial stack entry starts at the highest possible address. As information is added to the stack, it builds towards memory location 400. This location is defined as our stack limit. As entries are removed from the stack, it retreats toward its highest address. Finally, when all interrupts and traps have been serviced, the stack is back at its starting address. In some PDP-11 systems, there is a yellow zone located just beyond the stack limit. If the stack overflows into this yellow zone, the program is alerted. Corrective action can then be taken before the stack enters the area occupied by the interrupt vectors. In other words, the yellow zone acts as a buffer zone. It provides overflow space for the stack so that operations causing the violation can be completed. Then the program traps to memory location 004. Earlier in this study unit, we said that memory location 004 is reserved for one of the trap vectors. This vector contains a starting address which directs the processor to an error handling routine that services the stack overflow condition. It also causes the processor to load a new PSW prior to executing this error routine. If the stack advances beyond its yellow zone, it enters a red zone. When this red zone is entered, the program is notified that a fatal stack violation has occurred and the operation causing this violation is aborted. Here's an important point to remember. Whenever a red zone violation occurs, the old PC and PSW are stored in memory locations 0 and 2. A new PC and PSW are then taken from locations 4 and 6, and a hardware error trap is executed. We've now looked at these areas of memory. The first area is reserved for trap and interrupt vectors. The second area is occupied by the hardware stack and its accompanying yellow zone. What about the remaining area of memory? Well, this area provides storage for user programs as well as the system and utility programs. The system and utility programs require at least 4K of storage and are always located in the top 4K of memory so that they do not interfere with the user programs. It's now time for a short break. When you return, we'll discuss some typical memory operations involving data storage and retrieval.